Hey guys, Talon here, back with Lab 4 Oscillations. So yeah, let's get right into it. Okay, a little introduction. The purpose of this lab was to analyze the data associated with the motion of a spring mass system in which the mass is swinging and oscillating at the same time. The data that was collected is then compared to a computational model made with Newton's laws and the energy principle to see if they are similar and that if energy is preserved. So some of the fundamental principles that are used within this lab are Newton's second law, which is like the momentum principle, as shown here, where force equals mass times velocity over time, which is F equals ma. The energy principle is used, which the system is the mass spring, and the Earth is the surrounding. But as right here, shown here, is the energy principle, and the Hooke's law is also used in some of the calculation in the computational model. Okay, a little sneak peek, a little preview of the lab. The computational model matched the data collected from the experiment in both the y hat and the x hat direction, indicating that physics principles and fundamental laws can be used to predict this type of system's motion. To add, the data and computational model both showed that the integral principle was accurate as the total energy remained roughly the same throughout the entire experiment. So the actual experiment itself, a video was pre-provided to us, so that made everything a little bit easier. But like previously stated, the system is the mass and the spring, and then the surroundings are, well, I guess the Earth. Some of the knowns that we knew kind of coming in was that the mass was 0.402 kilograms, that gravity was 9.8 meters per second squared, that the spring constant was 6.83, and that the L naught was originally 0.13, and then the spring was like relaxed at a specific length. And then here is the data that our tracker put out, which is very similar to the one that was shown in the video. Okay, step by step in the computational sense. So we simply set up the video provided into tracker. We use the calibration stick to set distance to a given number, and then we set the axis as well. We played the video and we tracked the mass over individual frames to collect the X and Y data. And then we take the data tracker, put out, and download it into a CSV file. So the data that the video gave us, we then downloaded that into a CSV file, which then was later able to be used in GlowScript. So, like I said, we take that provided outline of the code and we input equation/given data to create a computational model of the experiment. Then we uploaded that CSV file into GlowScript, and then we compared the two separate things, so the real data and the computational data. Okay, so on a code and data comparison. So right here, starting on the left, is the code that we had to use to calculate it over the time. So we have like the initials with the energy, and it was really just energy final, so that's why we set it equal to that. But we had to use some update formulas. We had to use Hooke's law and other stuff like that. And then over here, we did more calculations, kind of inputting givens, and then also doing calculations with L and L hat in order to use it within the US or Hooke's law, the spring. So the code and data comparison, here is our data. So our data lines up pretty accurately, as you can see, in both the X and Y direction. Okay, possible errors. Possible errors could involve the tracking part. There could be slight tracking errors within the time frame. Air resistance was not included into this. It likely is not that much, but it still could have caused a little bit of error. This spring was assumed to be ideal, but in a real system, it's not going to be ideal. So that is one other source of error. And then the main thing was probably the initial conditions were slightly off. So the position / the velocity could have been off. So the what does it mean questions for your model. For your model system, is the energy principle satisfied? Justify your answer by discussing briefly your plots of energy changes. So the energy principle is satisfied by the fact that in the change in energy versus time graph that was given to us after we used the computational model with the data provided, it shows that the change in energy stays around 0 for the entire interval. So we showed that here, and you can see it like slightly increases a little bit, but it stays roughly around that 0 mark. And then using the data you obtained in tracker, make two separate estimates of oscillation periods. First, by estimating the period of oscillation for the X position data, and second, by doing it for the Y as well, and then compare the two estimates and discuss. So the best way to do this was just by taking two peaks of each of the graphs, so the X and Y graph, and then calculate the time between them. So for the X graph, the time between one peak to get to another peak was 1.7, And then for the y graph, the time it took to get to one of the peaks to the other peak was about 1.5 seconds. And these answers are very similar, which they should be, but they could also be slightly off, like they also are, due to the slight error when in the calculations like listed. So thank you. That's it.